Thank you, Raffaele. And now I would like to present to you the preliminary results obtained in our laboratory in terms of fatigue correct propagation in traditional aluminum zinc alloy, because it's a material can be classified as a lightweight material. There are a lot of metallic materials that are characterized by low values of the weight. For example, the alloys of lithium. But the lithium is expensive and is used much more in other fields like electronic one, so battery production and so on. Another one is the magnesium. Magnesium technology is very interesting. It's developing, but it is available in the world because it's taken directly from the sea, but suffer of a very dangerous problem because at the high temperature can take a combustion process like fire. Okay, 200 Celsius degree is surface. Aluminum alloy is a good response for now. I remember in the 80 years of the previous century, components designed in aluminum alloy was very expensive because the metallurgy of aluminum is not a pure metallurgy. It's produced by a chemical process, like by, for example, process. And it's an expensive process, not so much for the economical reason, but for the environmental reason. Now it's much more cheaper, and it's used for the construction of components commonly used in production of cars in automotive, for example, or in industry software, airplane, or other fields where the weight is important. So, as you can see in many components, the fatigue is the grit. It's the grit problem of the design of components. So, in this work, we explored the first results of the addition of nanoparticles in order to reinforce the behavior, mechanical behavior of aluminum zinc alloy. Firstly, a few words about the characteristics of aluminum. You can see that the resistance of aluminum is ridiculous. It's no good. You have to do something to improve this. And the solution is to generate something in the structure able to block the movement of the dislocations. The first one technique is to use an addition of other components, for example, copper, and use the property of the limit of solution to create the zone where the dislocation has been blocked. For example, in this case, we have a different diagram of aluminum and copper. You can see that we have a limit of solution. The maximum value is about 50%, for example. What happens if I hit the material in the alpha zone? It happens that all the atoms are perfectly solidified. Okay? Then, with a quenching, I can freeze this situation. But the increment of the resistance is not so high. Not so high because this location can move in this lattice without any problem. The structure is a cubic center structure characterized by a plane with high values of mass. Okay. What I have to do? For example, I can heat another time the material at temperature lower than the critical one. In this way, the energies are available and the diffusion of the atoms can take place in the normal time. What happens? Happens that the movement of the atoms thanks to the lower energy, that is the formation of this precipitate. Okay? How many times I have to stay at this temperature? The time necessary to grow the precipitated particles, achieving a size that can be comparable with the size of the dissolution. Okay? Which is the result. So, for example, you can see that the series 6000 alloy with this kind of thermal treatment, the resistance increased. The much stronger alloy is the 1775 alloys, which the values achieved is comparable to the steel, common steel. In this way, you can have a material can be substituted the steel, but it is much more light. Okay? What's the problem? The problem is that, oops, I have to heat. I need a furnace first. The components that I can do must be to not so much large. Okay, is limited to the furnace. Another problem is that if I need some joints by traditional welding, I have a problem because after the welding, all the process will be cancelled. What can I do? So this is the equilibrium diagram of aluminum and zinc. You can see that we have a very wide region of limit of solution, but it's used an alloy with a concentration of zinc around 5% for other reasons. In terms of morphology of a structure, you can see that is a received material without any heat treatment. You can see the presence of alpha phase, this one in white, in black, the beta phase that is rich in zinc. After the heat treatment is homogenized like this. So we try to change the treatment. Well, okay, I need some particles precipitated in the microstructure to block the movement of the dissolution. I can substitute the precipitate using nanoparticles. Dioxide, zirconium nanoparticles put directly in the melt without any heat treatment. After you can, if you can do other thing, you can perform it. But now, this is as received material. You can see that the microstructure is characterized by an oriented structure without it means that there is not heat treated progress. So this is the chemical composition. You can see that we use the traditional 7000 alloy with zinc, copper, and magnesium, and the resistance is too high. It's comparable with the resistance of the steel tube. So, what is the behavior in terms of crack formation? We use the three different load ratio, 0.1, 0.5, and 0.75, in order to understand the behavior in the changing of this parameter. So the frequency is 30 Hertz. Then we observe, we calculate the crack length using the angular method, and this value has been controlled by a microscope. The microscope is the dog here. the rose is the camera. So this is the first result. You can see that in terms of threshold is not so good. For megapascal root squared, meter is not so high. Then you have the first stage, the second stage, third stage, and so on. But this stage seems to be linear in this scale. This range. This linear is one that it could be the highest law, but the slope of this is not the mean. It's range. And here we have another region that is linear. This is the results compared with the different load region. You can see that the values of the threshold decrease, increasing the load region. The values of high values of ratio is very ridiculous. Just a little bit much more too. What happens in terms of micro morphologies? So this is the pictures taken on the surface of the space. And you can see that we have, so this is the pre-crack obtained by normal procedure in STM6 47. But here we have a region characterized by a dark green region that the intensity fades to the white. Here we have a sort of a white region, and then the static fracture at the end of the surface. This is the situation to R 0.1, 0.5, 0.65, 75, and the oops. And the white zone decrease in the loaded region. In terms of correlating the RDM delta K curves on the surface, you can see that the first and second stage characterize the first part of the structure, microstructure, then the white in all the cases. So we investigate what it happens when change the slope of the studies. Here, at the low values of delta K, you can see that the mechanisms are different from the different phases. This is the direction of the crack propagation. And at the end of the second one, we have always the same direction. Change the quantity, the difference between the different phases tends to be homogenized. In the last stage, the aspect seems to be much more flat, but increasing the magnification, you can see that we have the typical striation, fatigue striation, okay, but at high magnification. So consider the different load ratio. We have the same effect, but the zone characterized by a much more flat mechanism. Fracture mechanism seems to be much more important. And then the situation at the end of the second one is similar, with a difference. Here, there are an alpha phase characterized by sort of stairs fracture. It means that the fracture is not only along the direction of the venous fracture, but we are initiating a sort of secondary crack. Secondary crack that are much more evident here, except here. For high values of saturation, you can see that at the boundary from the first and second phase, we have a sort of a denomination. and so on. The second one, here, the presence of secondary crack there are not so rare. So, up to now, we have this conclusion that the crack flow behavior seems to be different to the traditional one in terms of the RDN delta K, and it could be attributed to the presence of the zircon dioxide. The phase responds in different way. It's normal because the beta phase is much more the beta phase is much more brittle than the alpha phase. The crack path follows the rotation of the laminated phase. It's obvious. Macromorphologies, the crack propagation, show a fading of the gray at the first and second stage. This is due to the difference of the Felix reactions. Can be catched just at the high levels of modification. In the sharp changing in grayscale between the second and the third stage. Why? Up to now, I have no answer for this. I think that the range of the zircon dioxide governs this variation of the slope in the variation of micro mechanisms, structure mechanisms. Thank you for your attention.